Greetings and welcome to a new video about inverters. In this example we will look at a design example for our 3-source multi-level inverter. Of course we will work out everything for this example also step by step in our calculations and also verify these in Matlab Simulink simulations. So we have the following circuit. We have a 3-source inverter in this configuration, which is a multi-level inverter. And what we have is that each VDC, DC voltage source here is 100 volts. We have a series RL as a load, which are shown here, the values, and we have a switching frequency of 60 Hertz. The first part is really a design problem. What we want is delay angles for these inverter switchings, alpha 1, alpha 2, and alpha 3, such that the third harmonic and the fifth harmonic components are eliminated from our load voltage. And we have also the modulation index of 0.81. So we have now several specifications here and we need to determine this alpha 1, alpha 2 and alpha 3. And once we have done that, we go to question B, C, D, E and we calculate the RMS load voltage, RMS load current, the THD for the load voltage and the THD of the load current. Okay. Now before we dive into the calculation, let's see pictorially what the waveform of the load is, of load voltage. You see here now the alpha 1, alpha 2 and alpha 3. These are the delay angles. And this is again the similar graph we have seen in the previous example, the staircase load voltage. So you see it starting from 0 in a staircase to VDC, and then 2 VDC and 3 VDC, and then going down in this similar fashion. And you go to minus VDC, minus 2 VDC, minus 3 VDC. And this is now, as we have seen also in the previous example, we see here multiple levels. So that's why it's called multi-level inverter. Calculations, now the Fourier series for the load voltage. But in this case, with a 3-source inverter is given by this expression again. What we need again is the amplitude of this Fourier series. And the fundamental frequency we have here is 2 pi f, which is then 2 pi times 60, which is then 100 pi radians per second. And the amplitude of the load voltage harmonics are given by this, which is now expressed here. And you see now here, in addition, another cosine because we have another alpha. So moving on and then calculating the load impedance, that is given by this. This is just a series combination of the resistor and the inductor here. So the amplitude of the load current harmonics are then given using Ohm's law. We know that is just the harmonic for the load voltage over the impedance, and that can be also expressed like so. And in complete sense we can also determine the load current harmonics using this formula directly. But let's now also look in great detail what we need to do for the third and the fifth harmonic component elimination. Now we need to eliminate those two harmonics from our load voltage and consequently from our load current. So we need to define or set that we have a third harmonic of the voltage will be 0 and also the fifth harmonic of our load voltage will be 0. So this is actually from this expression, from this formula of the load voltage harmonics. And we need the modulation index, which is 0.81, and the modulation index was given by this expression, and that can be also written like so. And that can be then reduced to this expression, so you can also use this directly. You see here the alpha 1, alpha 2 and alpha 3 already appearing, divided by 3 because we have now 3 sources. Also rewrite this, so we have now cosine alpha 1, cosine alpha 2 plus the cosine alpha 3 will be 3 times the modulation index. And this one will be then 0, that means this expression substituted as n is 3 here will be also 0. Now you can divide out this coefficient here, so you get now cosine of 3 alpha 1 plus cosine of 3 alpha 2 plus the cosine of 3 alpha 3 is 0. In a similar case for n is 5, you do the similar case and you get this expression. Now you actually see now here 1, 2 and 3 equations with 3 unknowns, which are the alpha 1, alpha 2 and alpha 3. But it is a nonlinear equation, so the set of nonlinear equations we have is this. And this is quite complex to determine that by let's say hand, etc. So we will use Matlab script for that, and we also use the Newton-Raphson method for solving this nonlinear equation. And I will show you that in this script here I have prepared. This is a script for solving this problem. So we have now here 3 unknowns. I call this here A, B, C. So alpha 1 is A, alpha 2 is B, and alpha 3 is C. And MI here is another parameter, which is our 0.81, so it's just a number. Then I define a function here. You see that define f1 with 3 unknowns here, and that is just this formula. The second one, f2, is again this formula, the second one. The third one is the formula where we have this equated to 0, so that's actually the following. So I replace this 3 times mi to the left side, so everything is then equated to 0. That is this equation. So this is for elimination of the third harmonic, this is for the fifth harmonic, this is to satisfy the modulation index. So 3 equations with 3 unknowns in a nonlinear fashion. Now for our Newton-Raphson method, we need to make an initial guess for our value. So we need to say what should be this alpha 1, alpha 2, alpha 3b. So just an estimate. If you of course have the estimate close to the actual value, you get your answer faster. So I said, okay, that could be maybe 50 degrees. The other one 30 degrees, which is 50 degrees, so this is just really random. And then also, this is just given in degrees, so I converted that in radians. So everything is converted now using this formula in radians. And I created here a vector that will have then the initial guesses or initial values I have guessed in this method. And I iterate this process 100 times. You can also do it 10 times or 5 times, but it can be of course made more accurate if you do that more often. So this is 100, so it's, in this case good enough to get a nice accurate result. Then we need to use derivatives. So this is really in the Newton-Raphson method required. I won't go into the detail of Newton-Raphson method, so this is just really what you need. So we then differentiate the first function with respect to a, that's given by f1a, so that's given here by this command. Similar case for differentiation with respect to b, and differentiation with respect to c. Similar case for the f2 and f3 here, so we have all 9 cases. Now, next part of the script is here, so we need to, you don't have to, but it could speed up the process. I convert my function I have defined here into Matlab function, so that will really speed up the process. You can see it also if you don't do that. So I will call this just not f1 but f11, so that is just my new function, but then Matlab function, so Matlab function and then f1. Similarly for f22, etc. So this is just to convert that, nothing more. And also convert all the partial derivatives in Matlab function. So I go to f1a and then convert that to f11a, and similar for f11b, etc, etc, etc. Now this is all done, and then I will iterate the process because I have said that I will do it 100 times. This is the Jacobian matrix actually created from these derivatives. So that's all here. You can see that. And this is the value I will have by doing minus the j, the Jacobian matrix, over this f, the matrix for all the functions. And that will give us some result. And then I said, okay, this is then something I need to then update that. So update the solution with a vector v, and then call that a new vector, and then get the new process and start it all over again, and then for ns2. And then at some point we will then converge to a final value. And that is, if you do that, if you run the script, and the script was called, in my case, Newton-Raphson method 3 variables and a v2. I have also the v1, which was a slower version. This is a faster version. And it will give me this. So I have a v, which is 0.2002. The other one was 0.4724. The other one was 0.9770. This is all A, B, C, or alpha 1, alpha 2, and alpha 3. Everything in radians. Then I converted that in degrees, so I can see that more clearly also for myself. So I just did it times 180 over pi, and you get these values. You see my initial guess for alpha 1 was pretty fine. It was 15 degrees, so I came up here at 11.5. The other one was also pretty close actually, so this is good enough for this case. So these are the exact or close exact values I need for my alpha 1, alpha 2, and alpha 3 in order to succeed, in order to eliminate the third and the fifth harmonic, and having a modulation index of 0.81. Okay, Let's now bring up the problem again. This is just a script to illustrate what we need for our alphas. We have now our 3 alphas, we can now move on. The RMS load voltage is again calculated using this general expression. We know in this case the following thing, that we have also symmetry here. So we can say from alpha 1 to alpha 2, I have here a part which is, let's say, a rectangle. I have exact same here. I have exact same here. And I have exact same here. So I have 4 times that. So I can divide the problem. So I will show you why I have done this like so. So 1 over 2 pi is in front. And now divide this integral not from 0 to 2 pi, but going from alpha to alpha 1 to alpha 2. But I know that it will be then 4 times, so that will be then 4 times. And then the value will be VDC, so I need to square that. But I see from alpha 2 to alpha 3, I see this will be here. This will be here, so 1, 2, and this will be also here in the negative part and also here. So I have again 4 times, but then the amplitude will be not VDC, but 2 times VDC. So I need to square that 2 times VDC. The next one will be then for alpha 3 up to pi minus alpha 3. I have it here. And next one I have all here. So then I have all the areas, and that's given here. So I need then to use the 3 VDC quantity squared. And this is now the expression I need to use to calculate the VO RMS. Now this is then the expression. You can see this is all evaluated. This is not really that difficult, I assume. So you can just see that you bring all the VDC squareds in front and then evaluate this integral. You get this expression. Now what I have done is I see that we have everywhere VDC squared. Here VDC squared, VDC squared. So in the square root, you can take it out and then make it just VDC. And I also process this 1 over 2 pi in this expression. So I see here 4 and then 1 over 2, that will be then effectively 2. I see here 16 over 2, that will be then 8. And of course the pi here in the denominator. And also for the 18 will be over 2 will be 9. And this minus alpha 3 will be then effectively minus 2 times alpha 3, which is shown here. Now, the next step is just to simplify this expression, because I can group the parameters. They are the same. I start with 9 pi, this alone. Then I see minus 2 times alpha 1. I see 2 times alpha 2, but I also see it here minus 8 times alpha 2. So that will be then effectively minus 6 times alpha 2. I have here then minus 18 times alpha 3. But I also have here 8 times plus 8 times alpha 3. So effectively minus 10 times alpha 3. Now this can be also written as shown, so I can divide this 9 pi over pi, so it will be just 9. And the minus, everything has a minus here, so I will bring up the minus here in the second term, and everything will be in the numerator positive, so divide by pi. The next step is also interesting to show what, let me go back. I actually brought this 9 outside the parentheses in the square root, so you can see that here. Then I need to divide this by 9, you can see what's happening. And then I can bring also this 9 outside the square root, because 9 is 3 squared, so you can get 3 times VDC. And that's shown here. And what I also did is that I brought this 2 outside the bracket. That means 2 times alpha 1 plus 3 alpha 2 plus 5 times alpha 3. That's all shown here. And interesting here is I also written this in a form that you recognize this for other multi-level inverter designs. You see here 3 squared, that is really 3 from the 3 sources. And you see here 3 VDC, which is this again the number of sources we had here in the configuration. So if you have 20, for example, it will be then 20 squared and then 20 times VDC. Or if you have 5, it will be then 5 times VDC and then here 5 squared pi. This will be different, so that is again another formula. Okay, now we have our expression for our 3 source multi-level inverter in this case, and we know the alpha 1, alpha 2 and alpha 3, and we need to use the radians here because this is given in radians, so we can substitute that, and that will give us, using the values, 220.5 volts. That is really the load voltage RMS. That's the first question, and this is now the table we will use for our later calculation. What we see is the harmonics 1, 3, 5, 7 up to 23. Here are the frequencies, so 1 times 60, 3 times 60, etc. This is the load voltage amplitude harmonics using this formula, just NS1 and then NS3. But of course, using the alpha 1, alpha 2 and alpha 3 we have calculated. What you see directly is also that the third harmonic and the fifth harmonic voltage amplitudes are 0, as we wanted, because we have designed for these alphas. Now the RMS values for each component will be then determined from taking this divided by the square root of 2. The Zn is calculated using this formula. Just take the NS1 or NS3 corresponding to that one. Omega 0 is our fundamental switching frequency, so that is 100 pi radians per second. The resistor and inductor is shown here, so you just calculate for each n and you get these values. This is calculated using Ohm's law as shown here, and this is calculated the load current RMS by taking this and dividing that by square root of 2. That's really straightforward, I assume. And what you see is interesting is, again, the third and the fifth harmonic are gone. Third harmonic is eliminated and the fifth harmonic is eliminated. Then the RMS load current will be given by this expression. You don't have any average value of the load current or load voltage, so this is only the harmonics, only also the odd harmonics. Okay, then we need to look at the odd harmonics. That's the first one here, third, fifth, seventh, and ninth, etc. So I go here and actually to infinity. And this one will be 0. And this one will be also 0. So we will actually reduce the harmonic distortion here. That's also the whole purpose of this harmonic control. I will add up to 15.922 amps. Okay. Taking this all together, A and B. Next question is the THD, the total harmonic distortion for a load voltage. Now we have the necessary information in this table, so we can calculate it right away using this formula. We know the load voltage RMS, we know the first harmonic of the load voltage RMS. That's actually shown here, so let's substitute everything and we get here 0.1244 or 12.44%. In a similar case for the THD for the load current, that's shown here, and that will give us, again using the first harmonic RMS of the load current and also the RMS load current itself, you get now 0.0131, which is 1.31%. This is quite small. And we will see that also in the graph that this is indeed the case and looks quite close to a nice sine wave for a load current. Okay, let's collect the values here and now also look at the simulations. This is the circuit drawn in the Simulink using SimScape elements. These are all the generators. I will dive into detail shortly. You see here the VDC, 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 each 100 volts. You see here the switchings for the top one, middle and the bottom one. So these are the generators for top, middle and the bottom switches. We have also the scope, so I can also show you the result later also in a minute. And we have here the values. So let me zoom in the values we have displayed here, because they are not maybe clearly seen. And you go here one by one, you see here the RMS load voltage, 220.5 volts as we have calculated. 15.92 amps we have calculated, very close to that. The THD for the load voltage is 0.1244, so exactly as we have. And this THD for the load current is 0.01307, so very close to what we have calculated. So this is all checked. That's nice. Let's now see the settings for our pulse generator for switching. That's actually the first one. This is for the top one. You see the pulse generator and also here in pulse generator. And these are configured in order to have this delay angle. So this delay angle of 11.4690 degrees need to be added here, but then using seconds. So how do we do that? You actually use this formula. Delay time, so in seconds, will be then delay angle, which is given here in degrees. Or I should say radians, divided by the radian frequency, which is our 2 pi f. So that is really the formula. So this angle must be in the radians and our frequency must be also in radians per second. A similar case for the pulse generator 3 and 4 for the delay angle alpha 2, and that's shown here. And also this is positive, this is negative. And for these two pulse generators, I need to go for the delay angle alpha 3. And the values are shown here for in time. And this is the formula we need to use actually in all these phase delays in seconds. Okay, let's move on and look at the waveforms in the simulator, but individual output voltages. So the VO1, VO2, VO3. That is actually nice to see because the series combination of these three output voltages will create our load voltage. And those are shown here. So VO1 in red, VO2 in green, and VO3 in light blue. And these are for the delay angles we have calculated for 11.469, etc. for these delay angles. Now let's go for the two labels, for red and the green one, and the blue one, light blue one can be also done, but this is just to check. So the first label 1 is given here as 5.31 times 10 to the power minus 4 seconds. How do we know that this is correct? Because then it is delayed. Now that can be calculated using this delay time, alpha 1 in degrees over 360 in degrees times the frequency of switching, and then you get 0.53095 milliseconds, which is very close to what we have here. So that is again verified that this is indeed switching at this alpha 1 as the time. The next one is for the this one for green. This is the second label, and that is now here 1.254 milliseconds, and that's actually shown here, very close to what we have actually. The next one is not labeled here, but that is also calculated here as shown here, so 2.5916 milliseconds. That's for the third one. And it's all here actually for the two labels actually shown here. Now let's now also look at the waveforms. Final one for our source current, load current, and load voltage. Those are also very important. So source current, load voltage. Now this is quite interesting because you see here the load current is very close and almost a nice sine wave. Of course, we see some sharp edges and transitions, but it is getting much closer to the nice signal we want at the output. Alright, this is our example considering the multi-level inverter design, having 3 DC voltage sources at the input. We have created or calculated the alpha 1, alpha 2, and alpha 3. These are the delay angles in order to eliminate the third and the fifth harmonic, and also having a specific modulation index. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics, so we can grow our community and also this channel. Thanks for your cooperation, and see you next time in another video.